this training. So function f is called the solution of a differential equation. The equation is satisfied when y is equal to fx, and its derivatives are substituted in the equation. And we need to determine whether y is equal to f. Y is equal to f to the e to the x squared. Solution of y prime equals 3xy. So how can we do this? So what I would want to do is let's take this as y prime actually. Let's take the y prime. So if y equals, in this case, 5 to the e x squared, or y prime should be equal to, when we take the derivative of this, we should use chain rule, I'm guessing. Yeah, we should get 10 e. I'm tweaking out. Nope, not this one. So we're going to move the derivative now. Yikes. So rusty on derivatives after doing so many terms. So we're going to have 10 x e to the x squared. So we've got that. And this is going to be, I guess, they refer to it as the left-hand side. So left-hand side equals that. So, okay, I get what we're doing here. Okay, interesting. So we get our left-hand side in this case. So left-hand side equals 10x e x squared. So we have y prime equals 3xy, right? So we know what our y is. Our y is 5e to the x squared. So I want to get this down to, I guess, one singular variable. I see what kind of we do. So we basically get y prime equals 3x times whatever my y is, so 5e to the x squared. So we're going to put these together. We get it's not really looking the same so far. They look pretty different, and this is y prime as well. So this will not equal that no matter what I do. I don't think so, because I would get 15. I'm pretty sure, right? Yeah. So when I simplify this, I get 15x e to the x squared, which is not equal. Sorry, no. So therefore, left-hand side is not equal to right-hand side. Therefore, not a solution. Okay, there we go. Now for our next question, since what value of r is y equal to, so we have y equals e to the rt, a solution of y, second derivative, plus 2y prime minus 3y equals 0. Okay, so let's do this. Solution of, so we have okay, interesting. So let's see. We have a y here, and interesting. So in this case, what if I took this y? If I have y like this, and I took it and I just plugged it in here, and I just took the second derivative, and then I just did this plus. So we do that now and see what happens. So it's just going to be e to the rt, but I'm going to be taking the second derivative of this. So take the second derivative of this. So how do I represent that? So oh, there we go. We can just do it on the right hand side. Okay, so just display it on the right hand side. Interesting. Okay. Let's just do that. Prime equals. Now if we use chain rule here, so chain rule would state that okay, the derivative is rt. R is a constant, so it would just be e to the second derivative, this is going to be equal. Do we use product rule? No way. It might be. Yeah, we do use product rule. So it would just be the derivative of e to the rt. I'll take the derivative of times r times r. So is that what they did? E to the RT times r times constant is 0. Forgot everything. I did this entire thing wrong. Because what would happen is, since this is 0, this entire thing should cancel. The constant is going to be 0. So all that's going to be left is e to the rt times r times r, so e to the rt r squared. There we go. Perfect. what our y double prime is, and so we can plug everything in here and see what would happen. So y second derivative is e to the rt, times r squared, plus 2 times y prime, which is e to the rt times r, and then minus 3 times e to the rt equals 0. So I don't know what to exactly do from here. So it's a solution of this. So that means e to the rt should be like a root or something. No idea. We'll see. Just see what that means. I think I see it saved somewhere over here. Okay. And then you have to factors. What values of r make left hand equals right? So they basically simplified it. And then e to the rt solutions. But what values of r? Oh, okay. So now we want to see what values of r. They're asking for what values of r. I didn't even see that. What values of r? Oops. What values of r? Then we should take into consideration by expanding everything. So we get e to the rt times r squared plus 2r2. Oh, well, it's going to be pretty bad. So I'm going to take it from them, and it'll be e to the rt. You can factor out e to the rt, each one of that. E to the rt is common. And then you would have an r squared plus 2r minus 3. So you'd have e to the rt. And you have an r squared minus, r squared minus, r squared plus 2r minus 3. That would make sense. Okay. And when we look at this, we definitely have our factors. And so we can get our factors. If we factor that to be e to the rt, yeah, sure. And we factor r squared plus 2r minus 3, just like we're going to factor, and we should get r plus 3 and r minus 1. So what values of r? R can equal negative 3, r can equal 1. So okay, that makes sense. So then you take this negative 3 and you plug it in. So e to the negative 3t, so therefore e to the negative 3t, and e to the t are solutions in this case. That makes sense. It's pretty cool. I like that. So now we know what it means to solve a differential equation. How do we actually do this? Well, in some basic, because it's like y prime equals to y, we can reason out the solution. It's if for example, if my y prime equals to y, then my y has to be equal to 2y squared. Correct? Hold on, wait. Not 2y squared, it's just y squared. My bad. Alright. Is it? Or is it x squared? I'm just tweaking it. K e to the 2. Oh my goodness. What? Listen, I don't know what it means, so I'm going to do it. Oh, okay, that makes sense. Yeah, that makes perfect sense. Yeah, I get it. You do have to put the constant. Don't forget about that constant. Okay, that makes sense because you would basically get 2 times the value, which makes sense because there's 2e and 2x. But I was thinking about it the wrong way. So. just erase right here. Let's erase this. You want to get something like y equals ke to the 2x, which makes sense. Because when we take, for example, derivative of y prime, right, you basically get 2 e to the 2x. So it's just basically 2 times whatever my original one was. So that makes sense. Ke to the 2x would make sense. I just want to say k. I think it was a k constant. Whatever. Worry about that later. It's the later problem. Ke to the 2x. Okay. Now, we have also had to sometimes solve problems using initial condition. The problem of finding a solution of the differential equation that satisfies the initial condition is called an initial value problem. Okay, so we have something called an initial value problem, which shows IVP. So what's happening in these IVPs? It's the IVP problem. So, problem of finding a solution of the differential equation that satisfies the initial conditions for the initial value problem. I feel this is an IVP. Sure. Is there anything else that is an IVP? So, okay, example, if I have y prime equals x squared. So, we already know how to solve some of these differential equations. Solutions, general solutions. So, if my y prime, in this case is x squared, whereas my y is going to be, if they're just working backwards, that's different. Okay, this is like straight up differential equation. It's not, we're not doing IVP anymore. What is going on? Where is that part then? I can't skip one part. So let's say, let's say an example. Let's say we had, I don't know, y prime equals, I don't know, x squared. Then if I worked to the integral of y prime, then this would give me, say this is this, then y would basically be whatever the integral of this is, which in this case is going to be, should be x3 over 3, or like 1 over 3x cubed. I think so. I'm just so forgetful here. Yeah, I think she should 1 over 3x cubed. But it's an integral, antiderivative. So we do 2. Yeah, but one thing I'm forgetting is that you should have a plus c. It's a family of functions, so you should have a plus c for those. Let's continue onwards. Let's look at result direction. So dy over dx equals x squared. Sure, that makes sense. The derivative is equal to x squared. Same thing as before. Then my y equals 1 over the x cubed plus c. Then let's add 7. 7 equals y is equals 7. I don't know where that 7 even came from. So it just said 7 equals that. So it's like y. Y0 equals 7. Okay, we stated that y0 equals 7. Then we could find a solution. That makes sense. It's fairly simple to understand. So it's the same type of idea. Before I said y prime equals x squared, and therefore my y has to be equal to 3x cubed plus c, right? Now, let's say we said y0 equals 7. Then in that case, when this happens, that means 7. Then I'll just do 7 equals to 1 over 3. Wait, wouldn't that mean everything else in that be 0 cubed? Yeah, it would be 0 cubed plus c. And so the 7 equals c. So now we found our c value. So whatever it's set to 0 would actually give us our c value. Very interesting phenomenon. It's happening in specific forms. So my equation would actually end up being y equals 1 over 3x cubed plus 7 in this case, which is fairly interesting. I didn't know about that. That's cool. Would it be? Yes. Okay. If we draw short line segments with slope f x, so we draw short line segments with slope. So we have a slope of f xy at several points xy. a direction of field. So what are we going to do about this direction field? So what we should do is we should understand how it works, okay? So if your function satisfies a relationship solution, so I'm not going to be worrying about drawing these. They said specifically that they're going to be multiple choice questions around direction fields, no drawing. So I should understand how each function correlates to it. For example, you can see these are slopes at every single type of thing. So for example, if I had like y equals sine x, right? Then you know how it kind of looks. We all know how a sine function looks. So the curves at certain points should match how it is, right? For example, this one, a general direction of this is like, it goes something around like this, right? We also have something that goes like that. So it's got a little bit of a curve. You can see it's going down. And this part, it goes fairly down. So, yeah. And here you can kind of see that it has a little bit of abnormality there. Something going on here. So if I shade this area around, we can see that, oh, this area is going this way, this area is going that way, that way, that way, that way, that way, that way, that way. Right? So it's a negative slope only in this area. So when it's like interesting. So we should be able to match functions by looking at changes or inconsistencies. That's what I'm trying to do for this. Okay. So here comes a difficult part where we actually have to put this into play. So here we have y prime. So all of them are differential equations, right? Because they have a x and a y type of idea, and we have the slopes of them. So okay, we'll start with a, which is y prime equals x over 2 plus y. Interesting. The first thing I can state is that we could potentially have some type of asymptote. Potential, I don't know, that's what I'm saying. Because when my y, let's say if 2 plus y equals 0, my y is equal to negative 2, if my y is equal to negative 2, then we're going to have some type of issue occurring. So I'm going to look for that, some type of variability at y equals negative 2. Okay, so let's look here. So y equals negative 2. Right here, we can see that it isn't exactly 0. Okay, y equals negative 2, it's going downward. Y equals negative 2. Interesting. You see 2 points are colliding, at one going from the bottom, going from the up. Y equals negative. Sorry, I'm looking at x equals negative 2. What am I doing? Oh my goodness. So this is y equals negative 2 right here. Now, probably not 1. Here, something weird is going on. You've got 2 arrows kind of colliding, one going this way, one going this way. This is a potential candidate. I'm going to put C for a candidate. And let's look at negative 2 again. This one looks normal, pretty normal, just following a flow. Probably not 3. 4, negative 2, you can see something. It's like curving around. So it's either 2 or 4 in my opinion. What else can I note about it? It's rational, yeah. Maybe I'm wrong completely. Let's just see what they're doing here. Okay, ooh. They've got a little bit of some examples here which I don't have. Okay. See, yeah, undefined y is equal to negative 2. So, yep. I had a good feeling it's this one over here. Yep. So, okay, we're gonna go back. We're gonna feel like we never did that. So, potentially, this is the correct one. Because you can see, like there's an arrow going like this and an arrow going like this. So, it should potentially be like a 0 value. Because, I don't know, if it's 2 things are colliding like this, you should get like a flat one. I don't know. That's my thought behind it. So, let's just get rid of that. Trig function, we have y prime equals cos x plus y. So the way I like to think about it, I want to look at a cos curve. Potentially not really worry about this for now, but let's look at a cos curve. Cos curve, it's something I'm trying to remember. It's like this. Hold up, I'm gonna look. Let's say y is equal to cos x curve, if we look at the y is equal to cos x curve, it's like a bell. So it's like goes up, down. And if I look at one of the specific features of it, we'll see that it is sinusoidal, yes, of course. But what it's supposed to be going up and down like a bell. Do I see anything going up and down like a bell? It just goes up and down like this and this. So I kind of see something like that here in number 3. See, we have something going up, and then I'm saying that this could potentially go up again. But that's just a relative idea what I'm saying. So you can see look at the curve ideology happening here, like it's going up and down, or like something curvy is going on here, like that, like that. So I'm saying that number 3 should be B. That's what I think. That's what I think from. Let's see. Yeah, yeah, it's B. Yeah, you can see that. Oh yeah, that's really smart to do. Actually, it's really smart to do. If we have a y prime in this case, or y prime, which was cos what x plus y, right? Let's say both our x and y is a value of 1, so it's cos of if it's both two values of 1, 1, 1. So let's look at 0, 0. Cos 0. Well, let me see how they do it here. Say we've got x0 y0. Cos of 0 is 1. So you could see that it is 1. I guess cos 0. It's kind of hard to tell, but 0, 1, potentially. Yeah. Okay. Interesting. Cos 0. Yeah, whatever. I mean, I understood what the curve looks like. I guess that's enough, possibly. Alrighty. Alright, so, okay, let's get this one done. So, I have to figure out what's special about this over here. Oh, there's some more to do here. Euler's method. Oh my goodness. Okay, alright. Okay, let's look at this. Cos x plus y. Okay. What do I see special about this? See. No, not that. What am I looking at? So, always result in positive slopes. Ah, that's pretty smart. Pretty smart. Okay. So, here's a cool part about this. We can also identify, like, so this thing, whatever the case is, will always be a positive. You have a square here, right? It's a square. No matter what the case is, it's 1 plus. So even if I have -2, we're going to get a positive value. So in that case, in ideology, we can conclude that this will always result in positive slopes. So it has to be this one. That's very smart. That is very, very smart. Oh my goodness, that is brilliant. Okay, and this of course has to be D, but why though? If I look here, it says y prime equals x, y. So let's say at 0, 0, say x equals 0, y equals 0. That means at that line in the center, right? So if we look at this line in the center, we can see what's happening. You can see these, if two arrows are coming in like that, it means they're going to 0. See that? So at this specific line, not even this one, only this one, from x equals 0, y equals 0, at that area, you can see what the arrows are doing there. It's like an interesting thing, it's a phenomenon that's going with the arrows. So, in that specific case, this seems pretty good. So, since many differential equations are hard to solve, can we somehow use numerical techniques to help us approximate the answers? We'll learn the simplest technique, Euler's method. So, this is like a numerical technique to approximate answers for differential equations. So, to approximate answers for differential equations, use Euler's method. We're going to go through it. Okay, so ultimately gives an approximation solution of a first order initial value problem. So dy over dx equals fxy, subject to y x naught equals y naught with step size h at x n equals x n minus 1 plus h, using the formula y n equals y n minus 1 hf x n minus 1 minus. This is going to be included in the formula sheet, but I just want to know what. Where n equals 1, 2, 3. Interesting. Okay. So here we've got like a curve which is going up. It looks very exponential to me. It looks kind of exponential. But it says find the approximate values. Is it exponential? But probably not. Okay. Initial value problem. Y prime is equal to y plus x. Y prime equals y plus x squared. Y 0 equals 1 at x equal to 0.05 using Euler's method is h equals 0.25. See how they do it. I have no idea how to do this. And I completely forgot. So let's look at what they're doing. So we have yn minus, which is y value, previous step, and this is a step size, and this is the slope at previous step. So idea, start at xo, y naught, so two initial positions, follow direction field along a start distance h. Stop, reevaluate direction to follow, continue, stop, reevaluate until you meet your destination. Cool. So so basically x equals 0.05. So that's where we want to stop at. And our step n is going to go to 0, 1, 2, 3, etc. So like so. So step n would go 0, 1, 2, up to like 3 or whatever. And our xn basically is going to go up to 0.5. So we're going to basically divide 0.75 by 3. And actually you can see the step size. This is going to be the step size. So we're going to start at 0.25, I'm guessing, whatever our step size is. No, we start at 0. We start at 0. Is y 0. Okay, and this is going to be 1. Straight up, right? That gives our initial. Y naught should equal 1. And then this is going to be 0.25, and then 0.50, and then we're going to get to 0.75, which is our final area that we want to meet at. Now, we'll do that. The exercise is not for me right now. I need to get through as much as possible today. So, we've got 0.25, 0.50, 0.75. So let's do this. So, what we're going to do is, let me follow the formula here, what they want me to do. So, the formula is y1, let me just like a different color, y1 is going to be equal to y naught, right, y naught plus 0.25 plus the step size, right, plus the step size is h 0.25 multiplied by f times x naught x naught y naught. So this is going to be equal to 1, which is the initial value 1, plus 0.25 multiplied by f of x o y o, which is going to be 0, 1 in this case, which is like the next thing to look at. 0, 1. X of 0, y of 1. X of 0, y of 1, right? So that's going to give us 0.25 in this case. Or no, wait, what am I saying? Not going to give us 0.25 to calculate that. And that's just going to be 1, 0, right? So it's going to be equal to 1 plus 0.25 times times 1 plus 0. If we just add these two together, which is going to be 1.25 times 1, so just 1.25. So, and then you're going to start at 1.25 then, right? I'm guessing at the next step. Yeah, wait, we start at y1 is going to be 1.25. So y2, so we got a y1, y2 is going to equal to y naught, which is 1.25, plus our step size, 0.25, multiplied by f of whatever these two values. This is where the tough part comes in. F of what? X naught, y naught. So in that case, it should be whatever we're are we incrementing? Yeah, whatever we're going to be incrementing by. We're going to increment these as well. The 0, 1 is going to be incremented. Okay, so 0, 1 is going to be incremented to 1.25. And, sorry, 0.25, 1.25, 0.25, 1.25, and so this is going to be equal, to 1.50 times f of 0.25. So it's going to be adding these together times, oops, what am I doing? I should do all these together. 1.25 plus 0.25 times 0.25 plus 1.25. 1.25 plus 0.25 multiplied by 1.50. Let me see how to do the calculations. We did 1.5 times 1.5. Sorry, 5, 2, 5, 7, 5, 2, 4. what am I doing? Just plug into a calculator. I don't know what I was doing here. So 1.25 plus 0.25 times 1.50. That is 1.625. Where is my pad? Oh, 1.625. I think. Did they get 1.65 as? Oh, they didn't. Only 1.25. 0.25. So we do 1.25 plus 0.25 multiply that by. I think this was an issue where they got this part of this thing wrong. I'm pretty sure the teacher said something about it. I don't know. But yeah, we'll do the next part now. Now for y3 equals, so whatever I got before, 1.625 plus 0.25 times my new increments, which is just going to increment this by 0.25 as well. It's going to be 0.50 plus 1.75. Do that. 1.625 plus 0.25, 0.50 plus 1.75, 2.1875. So this is approximately this, I think. Okay. So that's that. Okay. We'll do this as like a later problem, I guess. Later to do this later. Music got turned off. Okay, what I need to do next. Oh, there's the next one right here. Okay. F1 3. Probably might need to learn this, so I might do this question later on, like an Euler's method. Trying to solve that, but till then we should go to the next. No. This is it. Introduction to differential equations continued. So we're going to be looking at separable equations, non-separable, and word problems, like in and out word problems. Like salt in, salt out. These are potentially very, very famous for being very hard to do. I don't know. I just made that up right there. But I don't know. We'll have to see. I completely forgot how to do separable equations. This was a very early lecture. I just forgot. So we have to reignite the learning. Let's download that. I'm gonna get back to streaming in a bit. Let me just I don't know how to Okay, I don't know how to pause the stream. Maybe I just turn it into like private for now, for a bit. Okay, so let me just go back here. I think it's this one. Okay. Alright, so now we're going to be looking at introductory differential equations, continued separable equations. We just spent time solving differential equation graphically and numerically, but is it possible to get an exact solution? Recall that for some simple examples, we were able to figure it out. Y prime equals x squared solution that, yep. And equals y is equal to over 3x cubed plus c, and y equals 2s solution, y is equal to c e to the 2x, yep. Today we'll learn to solve a class of differential equations called separable. A separable equation is the first order differential equation in which the expression for dy dx can be factored as a function of x times a function of y. In other words, it can be written in the form dy or dx equals g of x times f of y. Which of the following differential equations are separable in this case? Interesting. So, if we look here, this one, is it separable? So, so wherever I have a, I know there's something about it, I'm just forgetting. dy, where I have dx on the right side. 1 minus root y dy.
Trump seizes on weakness, and nobody's weaker than Mark Carney. Carney sold out Canada when he moved his company's headquarters to New York, giving Canadian jobs to America.
You sneaky.
Carbon tax Carney. If Carney wins, Canada loses.
New Pringles Mingles. Airy and crispy. Try new Pringles Mingles.
In this video, we only want to have x variables. Equal to 2, and x is equal to 1. Since the bases are 0.
Introducing new.
So many advertisements. Okay, we're going to look at mx. So, considering it, this is the form that we want to make it in. So, if I can make, just get an extra sheet, I can create an extra sheet in between these two. And thinking about it, if I have any separable differential equations, I should just be able to write it in this form, which the form is n of y dy dx is going to be equal to m of x. Okay, so this is the form that separable differential equations can be written in. You can see that the y is on the left-hand side, x on the right-hand side. Cool. So, know that in order for a differential equation to be separable, all the y's in the differential equation be multiplied by the derivative, and all the x in the differential equation must be on the other side of the equal side. Okay. Sure. So it's getting multiplied by the derivative, and the other thing should be on the other side. We first integrate both sides with respect to x to get that. Okay. And remember that y is really y of x, so we can use the following sub. Apply substitution to the integral, we get both sides and substitute. Just as it would be a lot, we can perceive the method solving the differential equation. Mathematically calculate solving the differential equation. Well, we can write the differential equation as this: ny dy equals mx dx. So, however, if we separate the derivative as well, we can write the differential equation as this. Unless we can separate the derivative like that, but we can do for a bit, we can do the answer with less work. This is proven how to do this. So, let's do this. Solve the following differential equation. Determine the interval of validity for a solution. Intermediate value problem, sure. But let's just look at this. So ny dy dx with mx. So let's start with this though. Let's start with this y prime equals x over 1 minus root y. So y prime is equal to, so let me put question number 1. Y prime equals x over 1 minus root y. X over 1 minus root y. Square root y. So is this separable? Can I like divide this side by 1 minus root y? Yes, I could. Right, so potentially I'm thinking if I have y prime over 1 minus root y, I basically have my x on one side and the y's on one side. That's what I'm thinking, which makes it definitely separable. But I'll have to see according to what this is saying. Yes. Never mind, what am I saying? Okay, this is what I did this. My algebra is absolutely so weak. Oh my goodness, my algebra is so weak. What did I even just do there? Okay, so what should actually be done? Multiply both sides by 1 minus root y. So in this case, it's going to go away from here and just going to get moved to the other side. So this is separable. So let's just rewrite what I have, 1 minus root y. So it's going to be, let's just rename this as dy over spot that. We have 1 minus dy over dx. So what am I doing? No. Sorry. I have 1 minus root y. So I don't know why I have dx here. What is going on? That can't be correct. This is dy. Yeah. dy equals just dx. And we should have an x as well, right? X dx, correct. There we go. So this is a way to write it. This is in case this is separable. Okay, next one. Let's look at question number 2. Question 2 has y prime equals the natural log of x plus x divided by the natural log of y plus y. Okay, so we've got our thing kind of set up. I could potentially multiply by natural log of y here, and this is indeed going to be separable. So then I would have the natural log of y plus y multiplied by dy equals the natural log of x plus x times dx. Question mark? Is this good? Yeah, I just had to put it in brackets just for safety. And this is indeed separable. Okay, here we go. Now let's go to number 3. I mean, this is the fairly easiest part to understanding how separable and non-separable works. Then only you can target to like fixing this up. So next we have y sine x plus xy. It's a little bit more of a tricky one, but no, this makes sense. This makes perfect sense. This makes perfect sense because okay, that makes perfect sense. So basically, let's say we had something like this in this form, like y prime equals, what was it again? It was y sine x plus xy? Question mark? What's some of this? Nice. So we have something like this. Now, let's say I wanted to factor, if I took this in as one singular term, could I be able to factor this out? Y prime equals, like, take out a value of y from both because they have y is common between them. will be y sine x plus x, like so. I'm pretty sure you could. So this can basically be written as, say this is a dy. You divide this by y. Yeah, you could, because you distribute this, you basically get the same thing. Yeah, you get dy over y, and it's going to be equal to sine x plus x dx. So this is indeed separable. This is separable. Separable. Oh, there we go. It's another one done. That's good. Eventually, we're going to run into something that's non-separable. We're going to have issues. It's number 4. Okay. So, for number 4, we've got y prime equals x cubed plus 1 plus y squared, x cubed plus y squared. Now, I don't know exactly what the strategy for this should be. Oh, right. I kind of get the idea behind this, because your y prime is just dy over dx. That's the same thing as saying y prime, and you're just moving the dx to one side and you're keeping the dy to one side. So whenever you see a y prime, put dy dx. That's the way to solving anything. So, okay, I was a little confused now, getting a little bit better idea. Let's see here. Let's do this. Then there's some stuff on this, solving stuff. You have to use integration to solve it. Very nice, very interesting. Okay. Okay, so let's solve this one here. So, alright, let's do this one. So, alright. Let's say we had y prime is equivalent to x cubed plus 1, x cubed plus 1 plus y squared, x cubed plus y squared. Okay, so now what do we need to do? We need to rewrite this in a way and see if it's separable or not. So y prime would just be dy dx. I need to move all my y's to the left hand side and all my x's to the right hand side. So can I rewrite this in any way possible, thinking about this thing over here? So if I have x cubed plus 1, I do have x cubed happening. No, I don't have it happening here. But do I have a y happening here? No, I can't. So I can't really factor anything out. I can't really factor like a y squared out. But can I rewrite this in a better way? So I have 2x cubed, so that's going to be 2x cubed, right? And then I'm going to have plus 2y squared. Okay, I have 2 of these, so I'm just going to cross out x cubed, y squared, and all we're going to be left with is a 1 plus 1, which doesn't really matter to this case. Now, if I kind of look at this, can I divide this entire statement by 2y squared? What if I did dy, and this would just be, it would be dy, sorry, hold up, I was written format for that. Right, so it would be like 2x cubed, sorry, 2 dy over 2y squared, something like this, right? And we're going to have like is going to be equal to 2x cubed plus 1 dx, something like this. I don't know. Potentially, I'd say something, because we basically expanded it, put everything together. Thing is, oh, no, we can't do that, because we have y cubed x cubed multiplication going on here. Y cubed x cubed. 2, no, it'll be multiplication. X cubed plus 1. Okay, and then let's looking at that separately. So basically, somehow this entire thing can simplify into this thing, turns into this thing. It's a little bit of a thought process behind that, though. Because the thing is, you can't just put these together. It's multiplication, so you can't really just do that. Oops. Let's do this. Get rid of that. Okay. Okay. So, this is a term, this is a term, this is a term. So what they were kind of doing, they did x cubed plus 1. And I have a question. Maybe they did y to the 4 plus, I don't know. No, that wouldn't make any sense either. Because you can't really simplify anything further. I'm just seeing how. Do we have like some kind of difference of squares or something? No, not different squares. But they somehow got y. They have 2x cubed. Sure, they can factor out x cubed. But they can only take x cubed to that one. And they don't. Oh, they can't really take anything out. To put those in brackets, and then I took out an x cubed, so I'd have x cubed, and I have 1 plus 1. 2x cubed. X cubed y squared. Y squared. We could try to expand it and see what happens. So we'd get x cubed y squared, x cubed y squared, x to the 6 y squared, x cubed. This isn't really fun to look at. This is horrible. Maybe if I factored this in first with this. I don't know why I'm multiplying it. What am I doing here? Stupid as well. I don't know. I'm doing something wrong. I'll get it back.